So in the next series of presentations, we're going to drive toward a more and more quantitative analysis of what we've just talked about. And this doesn't in any way diminish the importance of understanding the character or the qualitative response of reactions to stress, but we'll find that we can actually calculate specifically values of K under conditions of concentration, of pressure, and we can calculate delta G quantitatively along that path that guides the reaction from its stressed position to its equilibrium position. So let's take one of our favorite reactions. Let's look again at this reaction of NO2 to form N2O4. And again, NO2 is this yellow-orange gas that is created in combustion processes and forms a dominant smog element over cities, particularly in the summer. And here we're going to employ a three-step process. We're going to use Le Chatelier to establish the direction of change, that is, the qualitative response of the system following stress as it drives back towards its equilibrium position. We can set up the reaction quotient Q because we can calculate it directly from our law of mass action. So we have C raised to its stoichiometric coefficient, D raised to its stoichiometric coefficient divided by the reactant A, reactant B, again according to the law of mass action. And then finally we adjust the concentration or pressures in the reaction quotient to reflect the quantitative extent of change and to solve the algebraic equation that results. That is, we want to start from a condition of equilibrium, apply a stress, and then calculate the final concentrations following the reestablishment of equilibrium. So let's take initial condition. We're going to work at 100 Celsius or 373 Kelvin, and we're going to start with a mixture that contains our reactant NO2, and the initial pressure is going to be 3.12 atmospheres, and the initial pressure of N2O4 is going to be equal to 1.50 atmospheres. And this is an actual experiment. The pressures and temperatures are correct. But then we're going to apply a stress, as you might have expected, since our whole analysis here depends on what happens when we apply a stress to an equilibrium state. And we're going to execute a tenfold isothermal expansion. That is, we're going to increase the volume of the system by a factor of 10. And the question then is, after we've applied the stress, what are the final concentrations? Now, we stated that the system was in equilibrium, so we recognize immediately we can calculate the equilibrium constant in terms of pressure. So we simply take the pressure of NO2 to its stoichiometric coefficient to the power of that. So we have 1.5 divided by 3.12 squared, or 0.154. So that's our equilibrium constant. Now let's apply the stress. We're going to increase the volume by a factor of 10, and we can immediately write the fact that our N2O4 pressure is a tenth of 1.5 atmospheres, or 0.15 atmospheres, and our pressure of NO2 is 0.312 atmospheres. And so we know that the first thing we want to know is what is the value of the reaction quotient immediately following the application of that stress. And so that's equal to 0.15, and we divide that through by 0.312, and we raise that to its stoichiometric coefficient, and that gives us a value of 1.54. Well, immediately in our mind we sketch the Gibbs free energy surface, and we sketch K and Q, and we know that at some point we've reached equilibrium, but we notice that Q is considerably larger than the equilibrium constant. So we immediately know that we're sitting to the right of the equilibrium point, and that means that the reaction is going to shift from right back to left as it seeks equilibrium. All right, so let's gather what we know. We know that immediately following the stress, we have Q is equal to 0.15, and that's divided by the square of the NO2 concentration, which is 0.312 squared, which gives us a value of 1.54. So we know then that we're sitting to the right-hand side of the equilibrium position, and that means in response to that shift, we're going to move from N2O4 back to NO2. Well, we know that our initial pressure is 0.312 for NO2, and our pressure just following the stress is 0.150 for N2O4. But we know that the fractional change of NO2 is going to be twice the change in N2O4. So we also know that we're losing N2O4 in this reaction, so let's take off a quantity x from that. But we know that we're gaining 2x of NO2 because of its stoichiometric coefficient. So we can calculate the equilibrium pressure then. That's 0.312 plus 2x, and the concentration of N2O4 is 0.150 minus x. But the new equilibrium point, because the minute that stress is applied, that system is scrambling to reestablish equilibrium, we know that we are going to drive back from the point of stress just following the application of that stress to the equilibrium point, and when we do that, we know that the equilibrium relationship between the pressures is N2O4 divided by the pressure of NO2 squared. And so when we do that calculation, that's 0.150 minus x divided by 0.312 plus 2x, the quantity squared. But we also know that that's equal to 0.154. Good. Well, when we work that out into a quadratic equation, we've got the quantitative relationship that 0.616 x squared plus 1.192x is equal to 0.135. Now, when we solve that, there are two roots. One root is x equals 0.1073. The other root is x equals minus 2.043. Well, as is always the case, the quadratic equation has two solutions, but in this case there's only one that's physically reasonable, because we realize that we are shifting from N2O4 to NO2. That means that x has to intrinsically be a positive number, because we're subtracting it to adjust for the response of that system to the implied stress. So that means that the value of x is equal to 0.1073. So we can immediately calculate the final concentration simply by inserting x into this expression and x into that expression, calculating the final equilibrium pressures.